Yes, sir.
Okay. Okay, students, welcome to Friday Happy Hour. And this is a week. You know what? I think I have the wrong one. Hold on. Let me do something real quick. Let's see. That was the one from last week. Let me share my screen again, and let me go get the one that I need. Okay. Let me see
No
here.
problem.
Let me go get it. Sorry about the mix-up. Let me see if it's this one here. There we go. There we go, guys. And sorry about the mix-up. Slideshow. Okay, now this is week 5, and this is a week where they separate into two workshops, the 1324 and the 1314. Eventually, I mean, writing exponential equations to logarithmic forms and vice versa, you're going to see it. I mean, the 1314, you're going to see it later on this semester. But for this week, that's what's going to be covered in 1324. But I also target this workshop also for the 0324, because a lot of students, they have a hard time with exponents. Okay, so I'm going to cover mostly exponents, and then towards the end, I'm going to show you how to graph, and also how to convert exponential equation to logarithmic form. Okay, so let's begin. So these are the topics that I'm going to cover today: exponent radicals and logarithms. Topics covered. So I'm going to cover exponent properties, converting radical expressions to exponential expressions and vice versa, simplifying radicals, exponential functions and the graphs, writing exponential equations into logarithmic equations and vice versa, and logarithmic functions and graphs. So to begin, you guys have to know some properties, exponent properties. And here's a notation, which means if m, n, and p are integers and a and b are real numbers, then this is a product rule. The product rule states if you have a to the power of m times a to the power of n, then it equals to a, you add the exponents, it'll be a plus n. This is property number 2. I'm just going over the properties, and right now, after I go, I think there are like 8 properties, or I believe there are 8 or 10. Once I go over them, then I'm going to give the property individually and give some examples. Number 2 is called the quotient property. If you have a to the m divided by a to the n, then you subtract the exponents. It will be a to the n minus n, and the a cannot be 0, because if a is 0, it's undefined. Property number 3. This is called the power rule. If you have parentheses a to the m, close parentheses, raised to another power. In other words, if you have a power raised to a power, then you multiply the powers. So it's going to be a to the n times n. This is called the power of the product rule. If you have parentheses a times b to the n power, then it's going to be a to the n times b to the n. And furthermore, if you have parentheses a to the n power times b to the n power, close parentheses to the p power, right? So you multiply the powers. Here, guys, we're applying the power rule, but with a and with b. You see, it's going to be p times n will be np, and p times n will be b to the np. And same thing with the quotient rule, power of the quotient rule. Okay. So if you have parentheses a divided by b, close parentheses, to the nth power, it's going to be a to the nth power divided by b to the nth power. And b cannot be 0, because if b is 0, it'll be undefined. And furthermore, right, like we did with the power rule. So here we have parentheses a to the m divided by b to the n, close parentheses, to the p power. It's going to be a to the n times p, right, because I multiplied p times the n, right, exponent times the exponent. And same thing on the denominator is going to be b to the n times p. Hey, students, at times, these might seem confusing by the way it's described on the rules, right? But this is the legal math notation. But once we begin doing some examples, it's going to be much simpler. Okay. Now this is called number 6. This is called the negative exponent rule. If you have a to the negative exponent, let's call it n, you make it positive by putting 1 over a to the n. In other words, it goes to the bottom as a denominator and it becomes positive. And again, a cannot be 0 because if a is 0, it'll be undefined. And furthermore, this is a real good thing to know here. Because in other words, if you have a fraction, right, raised to a negative exponent, all you do is do the reciprocal. Like, for example, a to the b to the negative nth power, it'll equal to the reciprocal, which is b over a to the nth power, and it becomes positive. That's very good to use, this one here. Number 7, 0 exponent. Anything to the 0 power is equal to 1. It doesn't matter what it is. Okay, so for example, here, a to the 0 power is equal to 1. And a cannot be 0. And this is number 8, the fractional exponent. You have to learn how to rewrite it from exponent to radical. So if you have a to the n divided by n equals to this is called the index. So the denominator on the exponent becomes your index, the a becomes your radicand, and the n will be the exponent. So a to the mn is equal to the nth root of a to the m. But this is wiser to use because this one, you can evaluate it without using a calculator. You can go from here to here, which is the same one as the nth root of a to the m, but I like to use this one better instead. And right now I'm going to show you an example of each one of those. And it has to be more than 2 because if n is 1, it would just be like a to the nth power, right? I mean, that's why it has to be more than 1, more than 2. Here are the examples, okay? Rule number 1, the product rule. As I go along and go over these rules with examples, if you have any questions, just raise your hand up, and in this way I can answer your questions. Okay, so here we go. A to the m. The a is called the base. This is my base, the a, and the m is the exponent. They must have the same base in order to apply the rule. What rule? The product rule here, for example, these have to be the same. Okay, so here we go. This is like the visual concept here, because you can actually see it, right? X to the third, right, is in blue, and x to the squared is in green. So x cubed is equal to x times x, right? Everything in blue, and x squared is in green, so it's equal to x times x. So x times x times x 5 times is equal to x to the 5th power. But this will be kind of hard to do if you have something like x to the 60th power times x to the 40th power. You're not going to put like x 60 times, right? Because that would take too long. That's why it's good to apply the rules. Okay, so what's a rule? By applying the rule, we have x cubed times x squared, right? We apply the rule, so we add the 3 plus 2, which is equal to 5. You can go from here, x cubed times x squared, to the actual answer, because you can add these in, right, in your head. 3 plus 2 is 5. But I'm showing you the second step, that way you know what's taking place. Okay, now this one, what do you think, what do you guys think it's going to be? Can somebody put it in the chat what they think it might be? Anyone? Very good, Jacob. It's going to be x to the 10th power. Same base, right? So we apply the rule. So x to the 10th. How about this one here? On this one, guys, be real careful before you answer. What do you guys think? Give you a hint. Are they the same base? No, right? So they're not the same base, so we cannot do nothing to them. Not the same base. Very good, my friend. Very good, Jacob. Hassan, very good. You see, it'll just be x squared times y to the 4th power. Okay, because they're not the same base. Again, in order to apply the rule, they have to be the same base. Okay. How about this one here? This one here, I'm going to cut it. Cut it in parts so you guys can see how the work is done. But you can do it all in one step. Okay. So for example, here's in parts. You're going to combine the coefficients 5 times negative 3, correct? And then times x to the 4th times x squared. So this will give you negative 15 x to the 6th. But you can go straight from what was being asked straight to the answer, because 5 times negative 3 is negative 15, and then we have the same base with x to the fourth and x squared, so we add the exponent. So again, you can go from the problem all the way to the answer. How about this one here? Can somebody answer this one for me, please? Give you guys a few seconds for you guys to think about it. At times, guys, when I'm in class, I'll say something like this: "Hey, guys, whoever gets this one right, I'll give you guys extra credit." And right away, everybody wants to participate. Somebody, guys? Or just give it a try. Jacob said x 6 to the x to the 9th power and y to the 6th power. Let's see here. Jacob, you're right, because -2 times -3 is 6, right? And then the x's have the same base, so 4 plus 5 is 9, and the y same base, it'll be y to the 5th power. Ms. Mesa, I believe you put negative, but when you multiply two negatives, it will give you a positive. Okay, but only the coefficient is not correct, but other than that, the x and the y to the 9th power and to the 5th power, they're correct. So always be careful, guys, with the negatives. When you have two negatives, right, when you multiply two negatives, will always give you a positive. Okay, when you have a negative and a positive, it's going to give you a negative. Okay, for example, this one here. This one here, it has a negative and a positive, right? So it's going to give us, does somebody want to try it? -30, yeah, -30 x to the 4th, y cubed. Again, when you have two different signs, right, you're gonna, it's gonna be negative, because negative and a positive will give you a negative. How about this one here, somebody? Oh, I gave you the answer there. I'm sorry about that. So there's my answer for this one, right? Because 3 times 8 is 24. X to the 4th times x to the 5th will give you x to the 9th. And y to the 3rd times y to the 1st power will give you y to the 4th. I believe, hey guys, I believe that's plenty of examples for you guys to get the first property correct. Okay, now let's go to the second property. This is called the quotient rule. Okay, for the quotient rule, again, they have to have the same base, right, in order for you to do the operation. So again, if you have the same base, you're going to subtract the exponent. So it's going to be a to the n minus n. For example, here, right, same basis. So we apply the rule. Equals x to the 3rd power. Number 9. Can somebody give me the answer for that one, please? Good job, Jacob. Good job. X cubed. How about the next one? On this one, guys, be careful, okay? You're able to do it. Very good. X to the -4. Okay, now, here, guys, x to the -4, right? Now, we can apply the negative exponent rule. Can be simplified. This is rule number 6. But I'll show you that one later because we're not there yet, all right? But this one can be simplified. Because most of the time, when you do your My Math Lab, they want you to simplify to the extreme. For example, that one's going to be 1 over x to the 4th power, which I'm going to show you rule number 6 when we get there. Okay, now this is rule number 3. This is called a power rule. When you have a power raised to another power. So when you have a power raised to a power, you multiply the powers. So for example here, x cubed times x cubed to the 2nd power. Let me show you what this means here, okay guys? This means x cubed times x cubed. You can do it like 2 or 3 different ways, but the best common way is to apply the power rule here. But I did it this way just so you see that there's always different ways to get the answer. Right, the same thing as x times x times x, right? Because x cubed is x times x times x, and x cubed is x times x times x, which will give you x to the 6th. But by applying the rule, we're just multiplying them out. Okay, so you can go straight from the problem all the way to the answer. How about this one here? Can somebody give me the answer on this one? It's going to be what, x to the 8th power, correct? Why is that? Because this is the same thing as negative x to the fourth times negative x to the fourth, right? So two negatives, when you multiply two negatives, will give you a positive. That's why it's going to be positive x to the 8. If you have negative y squared to the third power, it's going to give you, right? So how about this one here? Can somebody give me this one? Or try this one out? Is it positive or negative? Negative. Very good. Okay, but let me show you why. All right, so this, if you want, break it down. Negative y squared to the third power is equal to negative y squared times negative y squared, right? So negative y squared times negative y squared will give us y to the fourth. Then y to the fourth, right, times negative y squared will give us a negative y to the sixth power. Okay, so always kind of break it down if you're confused. Break it down, and that way it might be easier for you. Okay, now comes the power of the product rule, okay? So this is going to give us x squared times y squared. How about this one here? Can somebody try this one? What would it give us, guys? Good try, Jacob. Good try. But check this out. If you guys are confused on this one, break it down. Right? By applying the rule there. Right? So it'll be 2 to the third power times x cubed. It'll be 8x to the third power. Okay, how about this one here? This one here, guys, will just be x to the 3 times 2, right? Which is 6, and y to the 4 times 2, which is 8. This one here is going to be negative 3 to the third power, which is negative 27, and then x squared times 3 will give us x squared to the power of 3 will give us x to the 6, and y to the power of 3 will give us y to the third power. But how? How do we get this? So again, if you're confused, you can always break them down, right? So this means it's going to be negative 3x squared y times negative 3x squared y times negative 3x squared y. So negative 3 times negative 3 will give us 9. 9 times negative 3 will give us negative 27. And x squared times x squared will give us x to the 4th times x squared will give us x to the 6th. And y times y times y will give us y cubed. Or you can do it this way, right? So cube, it'll be negative 3 to the 1 times 3 because negative 3 is, there's like a 1 there. And x to the 2 times 3. And y to the 1 times 3 because there's like a 1 there on the y, but we don't put it there as an exponent. Which will give us negative 27, x to the 6, and y cubed. There's always different ways to get the answer. It all depends on how the student thinks because we all think different as students. Some students might get it right away by going from here to the answer, but some need to break it down, and there's different ways to break it down by using some of the rules that I already explained. Okay? There's always different ways to get your answer. This is rule number 5, the power of a quotient rule. So this will give us x cubed over y cubed, right? Because by applying the rule, there's like a 1 there for the x, so it'll be x to the 1 times 3, which is x cubed, and y to the 1 times 3, which will give us y cubed. I'm sorry about that one. Let me go back a little. Previous and previous. So here, it's going to be x to the 2 times 5 and y to the 3 times 5, which will give us x to the 10th divided by w to the 15th power. Okay. Now, we're going to do the negative exponent rules and zero exponent rule. So remember, if you have a to the negative exponent, it's going to be 1 over a to the positive exponent, I mean, whatever the exponent was. So here it was negative n, so it's going to be a to the nth power on the denominator. So how do we convert that to a positive? It's going to give us 1 over x to the 5th power. How about 3 to the negative 2, right? It's going to give us 1 over 3 squared, which will be 1 over 9. Are you guys okay up to this point? If you guys okay, just put yes in the chat for me, please. That way I know that you're understanding the material. Just put yes in the chat, please. That way I know that you're okay. Anybody else? Are you guys okay? Okay, let me continue then. Thank you, guys. Thank you. Okay, now, so let me continue with number 22. Thank you, Erica. Thank you, Sebo. Okay, now, hey, guys, remember on this one, we're gonna apply, right? We're gonna apply the when you have a fraction, right? We're gonna apply this becomes a reciprocal, and then this becomes positive. Right, the reciprocal becomes positive. Okay, now here's the reason why. Why is that true? Okay, because of this right here. If you have x to the negative third power, right, the rule is to put 1 over x to the positive 3, right? So then this is the same thing as 1 times, right? Because remember, division becomes multiplication, and the second fraction you use the reciprocal, right? So that's what we did here. So 1 times y divided by x to the third power will just be y to the x to the third power, you see? But it's much simpler when they give you a fraction to the negative exponent, just do the reciprocal and make the exponent positive, you see? So we can go from here to here without doing all this work. You see? So now, how about this one here, right? So here's an example. So I'm going to go straight to the answer. So the reciprocal and make it positive. Now it's going to be 5 squared divided by 2 squared, which will give us 25 over 4. Hey guys, all this material is crucial for 1324 also, and also when you get to if you're taking 1324 and you have to take more classes, you have to take 1325. That's for the students that are going for business or for accounting, and you have to know most of the material here about exponents and stuff. Okay, this is a must that you have to know. So that's why I decided to do most of this PowerPoint of the workshop for you guys to get a practice on how to simplify exponent, and by using the rules. So here comes the zero exponent rule. Anything to a 0 power is 1. X to the 0 is 1. Parentheses 5x y z to the 0 is 1. Anything to a 0 power will always give you 1. Okay. Okay, now here comes the fractional exponent rule. This rule is also a must for future courses. Okay? If you have a to the power of m divided by n, right, is equal to the nth root of a to the nth power, or parentheses the nth root of a, right, close parentheses to the nth power. So all these are the same. Now, what is the vocabulary here? The n is called my index, or the root, which will be your denominator, right? This will be your denominator when you go back from a radical to exponent, to exponential. That's your n. The a is called a radicand, which is a base, right? This is a radicand, which is a base over here. And the m is just the exponent, which is your numerator. Okay? And this is called the radical symbol here. So you go, so this is called my base, right? This is called here it's called the radicand, but here it's called the base, right? The base is the base. The n is the index, but here's the denominator. And the m is a numerator, right? The numerator, but here is going to be the exponent of the radicand. But you see equal to that right there. Okay, so how about this one? We have to convert it from exponential to a radical. So the denominator, the 3, is my index, right? And we have to put the 1 there because x to the first power will just be the same thing as x. This one here, right? So the 5 is going to be my index, right? That's my index, and it'll be x cubed. If you have parentheses, 3w close parentheses to the 2 power, this whole thing inside, guys, is my radicand. So my denominator becomes your index, and the numerator becomes your exponent. Okay, now they're going the other way around. Okay, now here they're going from exponential to a radical, and here we're going from a radical to exponential. So this 8xy, the whole thing is going to be my a, right? And the n is going to be 7, right? Because that's the index. And the m is going to be 2. So it's going to be 8xy, right? That's my numerator, which is my m. And the 7 will be my denominator, which is my n. Okay, from here. Okay, on this one. And then here, we have to be careful, okay? But if it doesn't have nothing there, it's going to be this all together because it's inside the radical. So it's going to be 6 parentheses 6x close parentheses to the 1/4 power. Okay, but now here's a common mistake that students make. They say that this is equal to 6x to the 1/4 power, which is not true. Because the whole 6x, right, the 6x is like my a. It's the whole radicand. Because 6x to the 1/4 power is the same thing as 6 to the 4th root of x. This is what this is equal. You see, but if you notice, the whole radicand is my 6x. That's why we put it here in parentheses. It's all together. Okay, so please, guys, watch out with those common mistakes that students make. Now, simplifying radicals. Okay, for simplifying radicals, you guys have to know basic roots, such as square roots, cube roots, and maybe also fourth roots. But the cube roots and fourth root to a certain root. Okay, right now I'm going to show you what you need to know. For example, for the square roots, you need to know like the square root of 1 is equal to 1. Square root of 4 is 2. And so forth, right? 9, and then 16 is 4. You have to know at least all the way to 10, or maybe perhaps even 12. The more that you know, guys, the better it is. You see, I went all the way to 10, but the more that you know, the better it is for you. So these are called perfect squares, or the square roots, right? So the square root of all these is equal to the number here on the right. So for example, the square root of 36 is 6, the square root of 49 is 7, the square root of 64 is 8, the square root of 81 is 9, and the square root of 100 is 10. Now these are the perfect cubes here. The cube root of 1 is 1. Why? Because this is what this means here. Okay? Let me cut it down for you guys. This means what two numbers multiplying with itself will give me 36. That's why it's 6. Same thing over here. What two numbers multiplying by themselves will give you 49. That's why it's 7. So same thing over here with the cube roots. One number multiplied by itself 3 times will give you 1. So it's 1 because 1 times 1 times 1 will give you 1. Now here, one number multiplied by itself 3 times will give you 8. The answer is 2 because 2 times 2 times 2 will give you 8. These are called perfect cubes. And the cube root of 27 is 3 because 3 times 3 times 3 times will give you 27. At least know all the way to the square root of 125, I believe. The cube root of 64 is 4. At least know up to that much. And the more that you know, hey guys, the better it is. For the fourth roots, at least know all the way to I think to 3, to the fourth root of 3. I mean of 81. You see, guys, at least know this many here. Know all the square roots, all the cube roots, and all the fourth roots. At least know up to that point. Okay, now examples of simplifying a radical. Okay, at times, guys, when they give you the square root of 24, you guys should know that this is not a perfect square, right? Because this is squared because the index is 2 there. When there's no index, the index is 2, which means a square root. You see, you notice 24 is between the square root of 16 and square root of 25, so I know it's not a perfect square. So what do we do then? We have to get the factors of 24. You see, is 24 a perfect square? No. So find factor of 24. 1 times 24, 2 times 12, 3 times 8, and 4 times 6. So from here, what's the largest perfect square? The answer will be 4. I mean, which is the greatest perfect square, which is 4. That's why I'm going to reduce that one. It's going to be the square root of 4 times the square root of 6, which is square root of 4 times square root of 6. The square root of 4 is 2, and that stays how it is. So this is my answer, guys. That's the simplified version. Hey, guys, you'll be, at times, guys, I'm amazed how many students, when they reach, say, for example, 1325, they have a hard time with, like this. Okay? So please, guys, you can always go back to this PowerPoint or this recording to understand these, how to simplify radicals. Okay, let's do more examples. So that's your answer. Okay, now, if you guys need more examples, guys, then perhaps you guys can get with a tutor, okay? Or maybe see me doing Sunday numbers. For Sunday numbers, it's from 9 to 10 for 1324 and 0324. Okay, so perhaps join me and I can help you more there. But if you want, afterwards, you can get a tutor to help you how to simplify radicals. So examples of exponential functions. Okay, now this is now related to 1324. Okay. These are examples of exponential functions. You see, you have a power to a variable, and most of the time it's going to be x. These are all examples. For example, f of x 2 to the x power is an exponential function. G of x 750 parentheses 1.05 to the x power is also an exponential function. 3.6 to the x power is also an exponential function, and 4 to the x plus 3 is also an exponential function. We call it a to the mn, right? A to the mn means the mn is like a radical right there. It's like the exponent. Okay, so it's going to be the same thing as a to the x power. So now we're going to be graphing exponential functions. And again, this is my base. And the exponent is a variable. Most of the time, it's x, but at times they can use y. They can use anything they want that's a letter or a variable. Okay, now, it has to be more than 0. Okay? With a being more than 0, you apply the rule. So here, guys, this leads to graphing. Okay? Because we're going to be graphing. You have to know how to graph in 1324, how to graph exponential functions. So when you graph exponential functions, you can use any point that you want, but these are the most common points to use. You go from -2 all the way to 2 or to 3. It all depends on the base here. If the base was like 4, you're not going to do 3, right? Because 4 cubed is 64. That's too much, and more likely isn't going to fit on your paper. So these are the most common numbers to use. Okay, when you're graphing exponential functions. So how do we do that? We're going to draw ourselves a little table. That's my x, and this is my f of x, which means this will be my y. So I'm going to put all the values here for x. -2. When x is -2, it means that we're going to evaluate the function f of x equals to x when x equals 2. You see that? What that means? That I'm going to plug in a 2 for every x, but a -2. So here, guys, we apply the negative exponential rule, right? So this becomes positive, but it goes to the denominator. So 1 to the 2 squared is equal to 1/4. So when x is -2, y is 1/4. Okay. Now let's try -1. So we're going to evaluate f of -1, right? So 2 to a negative first power is equal to 2 to the equals 1 divided by 2 to the first power is equal to 1/2. So when x is -1, f of x or y is 1/2. Now let's try 0. F of 0 means we're going to plug in 0 for the x. So anything to a 0 power will always equal to 1. So when x is 0, y is 1. Let's try 1. F of 1 means I'm going to plug in 1 for the x, right? For the x right here. So 2 to the first power is equal to 2. So when x is 1, y is 2. Now let's see. Now let's evaluate f of 2. F of 2 will be 2 squared. So 2 squared is equal to 4. So when x is 2, y is 4. And lastly, when x equals 3. So we're going to evaluate at f of 3 equals 2 to the third power. 2 to the third power is equal to 8. So now, this is my graph. Okay, check this out. I wish I could have done it better, guys, but but I mean with animation, but I couldn't do that with animation at this point. I actually need to improve on some of my PowerPoint skills, but I'm getting better. For example, how do we graph this one? If x is -2, right? -2 is right here. So 1/4. So 1/4 means that I'm going to cut the first unit from 0 to 1 in 4 places. You see there's like 1, 2, 3, 4. So 1/4 will be about right there. And if you notice, if we pick more negative numbers, right? I mean, say we chose -5, -4, -3. Eventually, it's going to be real close to the x-axis. So that's why it's always wise to use something like from -2 all the way to 2, or maybe even all the way to 3. Okay, but like I said, it depends on the base, depending how far you get here to plug in the values for x. So again, when x is -1, right? This is -1. It's about 1/2. You see, there's about 1/2. When x is 0, y is 1. There's a 1. When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. You see, guys, that's why I don't want to use 4, because if we use 4, 2 to the 4th power will be 16, will be way up here, right? And like I said, it'll be out of range on your paper. But if this continues all the way to 16, it'll be something like right about here. Okay? That's how you graph exponential functions. Okay, now exponential functions and the graphs. I'm going to show you here the characteristics. Okay, you have f of x equals a to the x. That's if a is more than 1. If a is more than 1, this is called growth, exponential growth. And these, you can use them like exponential growth. When something grows exponentially, like say money in the bank, and at times it grows exponentially. These are examples when, like for example, I like to use this example. I mean, like the virus, right? When a virus is there, infects some people, right? So the virus begins to grow exponentially because every person keeps infecting another person, and he keeps growing and growing and growing and growing. And when I believe on the exam, for exam 2, I do an example of the coronavirus when it started, and also how long it will take to reach so many people infected. So that's where we can use exponential growth. But anyway, these are your characteristics. The graph is above the x-axis, right? This is my x-axis, so everything is above. It never crosses the x-axis, this graph here, this is called also the parent function. The y-intercept is always 1. Why is it always 1? Because anything to a 0 power is always 1. That's why if you plug in 0 for x, right, it doesn't matter what the a is, it's always going to be 1, because a to the 0 power is 1. Say this is 5, 5 to the 0 power is 1, so anything to a 0 power will always be 1. That's why the y-intercept will always be 1. And the graph climbs steeply to the right. You see, it keeps going to the right. I mean, steeply, it goes to the right. The negative x-axis is the horizontal asymptotes. And the larger the base A, the more steeply the graph rises to the right. So if A is bigger, the graph begins to go something like this, closer to the y-axis. Right, I'm going to show you an example. You see here it is. You see, for example, this is, say that is 2, right? Say, for example, 2x, the one that we graphed earlier. It was something like this, 2 to the x power. As the base increases, right, 3 and 10, the graph begins to go towards the y-axis. You see, it grows exponentially. So the bigger the a, the bigger the growth. Okay. Now, what happens when a is between 0 and 1? So this will be the graph. This will be the graph when a is a fraction between 0 and 1. This is considered exponential decay. How can we use exponential decay like in real life? For example, at times when let me see here. I think when fossils were found, right, the fossils begin to decay at a certain pace. So we can use some type of exponential function, decay function, to see how long the bones were completely like 100%. So this means also they can use in forensics when somebody dies, right? They can put the body through a machine. Everything is there 100%. But as time passes, right, the body begins to decompose. That's why we use exponential decay. Something's decaying, it's decreasing. Okay? And here are the characteristics. The graph is above the x-axis also. The y-intercept will always be 1. But the graph falls sharply to the right. Okay, it's going to be falling sharply to the right. You see, to the right, it falls. The positive x-axis is the horizontal asymptote. Okay, so this is my horizontal asymptote right here. I mean the positive one. I believe on the exponential, it was the negative x-axis. This axis was the asymptote here. The smaller the base A, the smaller this base, the more steeply the graph falls to the right. Let me show you what it means by that. So, for example, right? So this is 2/3, right? 2/3. The graph is something like that in purple. You see now y to the 1/2. If A is 1/2, right? It begins to go towards the right here, towards the y-axis. The smaller the A. You see, 1/10, right, is real close to the y-axis. So, for example, if you had something like 1 over 100 to the x power, it will be something like this, real close to the y-axis. So these are the characteristics. Okay, now let's graph g of x equals 2 to the negative x. Okay, so to convert it, right, this will be equals, right, so to make the negative exponent to a positive, we put 1 over 2 to the x power, and it becomes positive. The x becomes positive. So this is the same thing as 1/2 to the x power. So now let's graph 1/2 to the x power. So again here, guys, I'm going to plug in the values, right? I'm going to show you how they got these values here. So for example, if x is -3, right? I'm going to plug -3 to the 1/2. Which means, right, remember the observation that I showed you last time, right? Instead of putting a 1 over 1/2 to the third power positive, you do the reciprocal here. Remember that? And then this becomes positive. That's why the answer is 8. The y is 8. And if you keep repeating the process, right, if you repeat the process for all the x values, these will be the results here. Okay, repeat the process for all these. This will be the result. Now, here's how you graph this one, right? So at -3, the answer is 8. Right there. At -2, the answer is 4. At -2 for x, the y is 4. At -1, right, the answer is 2. The y value is 2. At 0, like always, 0 will just be 1. When x is 1, y is 1/2. Right there. When x is 2, y is 1/4. Right there. When x is 3, right, it'll just be 1/8, right? They don't even show it there because it's going to get closer and closer and closer to the x-axis or to 0. So this is how the graph would look. Okay. Now let's do logarithms. Until the development of computers and calculators, logarithms were the only effective tool for a large-scale numerical computation. No longer needed for this purpose because now we have calculators. Definition of logarithm to a common base. The base is always 10. For example, y equals log of base 10 of x is the same as y equals to log of x because if there's no base, guys, if they don't have a base, it means it's base 10. Just for example, when you have x, right, you can say 1x, but they don't put the 1 in front of the x. We just know it's x. Same thing, here with a base. No base, it's base 10. Which means 10 to the y equals x. Now let me show you how that is. So again, there's no base there, it's going to be base 10. Okay? Simplifying without a calculator. Log of x or log of base 10 of x. This is how you read it. To what exponent must 10 be raised to get x? For example, 10 to what power will give you x? Let's do the example here. This is base 10, right? So 10 to what power will give me 100? The answer is 2, because 10 to the second power will give me 100. Now here, this means what base? 10 to what power will give me 10,000? The answer is 4, because 10 to the fourth power is 1,000. This is the way you're going to be doing logs, okay? But it's easier to use a calculator. But for now, it's good to know it also without a calculator. Because at times there's some logs that are not perfect, so it's going to be a decimal. So you cannot do it without a calculator. A calculator is crucial. But for now, these are basic ones that you can do without. So for example, here it's saying 7 to what power will give me 49? The answer is 2. Here, same thing. 3 to what power will give me 27? The answer is 3. Okay. Now let's write exponential equations into logarithmic equations and vice versa. This is also crucial for 1324. Definition of logarithm to the base a. So y equals to log of base a to the of x means a to the y equals x. Write each logarithmic equation into an exponential equation. So you're going from logarithmic to exponential. Okay, here's how you do it, guys. Right, so it's always good to put the definition here on the bottom. So I have to go from logarithmic to exponential. You have to know what the a is, what the x is, and what the y is. If you notice, my a is equal to 9. My x is 81. My y is 2. Now you go here and just put right 9. The a is 9. My y is 2. And my x is 81. Now write each exponential equation into logarithmic equation. Now they're going the other way. 5 cubed equals 125. So then you get the definition of the exponential. Put it underneath it. So here, guys, right? You have to go from exponential to a logarithmic. So you have to know what the a, x, and y is. So my a is 5. My y is 3. And my x is 125. So then it's going to get, right, my y is 3, my base is 5, my a is 5, and my x is 125. Or you can reverse it. Log base 5 of 125 equals 3. Okay, now in order to graph without a calculator, must convert logarithmic equation into an exponential equation. So we have to learn, I'm going to show you how to graph logarithmic equations. So I have to convert it to exponential, right, by using the properties or the definitions. So for example, graph y equals to log base 2 of x. So this is my base is a 2, the y is your exponent, and the x will be equal to x. So this is how you convert it or simplify it from logarithmic to exponential. Same thing with the graph here, because now you're going to graph this one here. But instead of using the values for x, you're going to put in for y. Because if you put in for x, they're going to be kind of difficult to get. But you can get the values for y if you put the values for x, but it's going to be much harder. So that's why let's play smart and put all the values for the y. Now we do the same thing as before. So if we plug here -2, right? -2 will give us 1/4. If we plug here -1, right? 2 to a -1 is the same thing as 1 over 2 to the first power, which is equal to 1/2, and so forth. So to graph it, guys, like I said, I'm still trying to improve on my PowerPoint skills. But anyway, this is the one that we did earlier. Y equals to 2x. Now this is my logarithmic. These are called inverse of each other, right? These are inverses. But anyway, that's another topic. But here, guys, is how you graph this one here. When your x is 1/4, right? At 1/4, if that's 1/2, 1/4 will be about right here. X is -2. When x is 1/2, right there's 1/2. If you go down, x is -1. I mean, y is -1. When x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. And when x is 8, y is 3. That's how you grab those. Okay. So this is my exponential, and this is my logarithmic graph. Hey guys, that's it for this PowerPoint. And I really went kind of slow because I don't want to lose nobody. and hopefully this this PowerPoint was informative. I know that that this PowerPoint is being recorded, right? But if you want the PowerPoint itself, that way you can have it. Just send me an email, and I'll be more than happy to send it to you. Okay? I'm going to put my email in the chat, just in case you want a copy of the PowerPoint. Send me an email, and I'll be more than happy to share it with you. Thank you.
Alrighty. Thank you so much to Mr. Sassi for presenting today. Thank you to the audience for coming and being a wonderful audience. We hope you have a great fall semester, and know that there is online tutoring, and as well as you can go to face-to-face tutoring to receive assistance on these topics that have been covered today. And I would like to invite you guys to next week's TVE events, Friday at 1 p.m. The academic success will be presenting, as well as at 3 we will have the Happy Math Hour event, and we will be covering synthetic division and complex numbers on the 1314 room. And then for us, the 1324, we will be covering solving exponential and logarithmic equations. So I hope to see you guys next week.